So in this whole process, where does intelligence originate, would you say? So if we look at things that are much less intelligent than humans, and you start to build up a human through the process of evolution, where's this magic thing that has a prediction model, or a model that's able to predict, that starts to look a lot more like intelligence? Is there a place where Richard Dawkins wrote an introduction to your book, an excellent introduction? I mean, it puts a lot of things into context, and it's funny just looking at parallels for your book and Darwin's Origin of Species. So Darwin wrote about the origin of species. So what is the origin of intelligence?
Yeah. Well, we have a theory about it, and it's just that, it's a theory. The theory goes as follows. As soon as living things started to move, they're not just floating in sea, they're not just a plant, grounded someplace. As soon as they started to move, there was an advantage to moving intelligently, to moving in certain ways. And there's some very simple things you can do, bacteria or single cell organisms can move towards a source of gradient of food or something like that. But an animal that might know where it is and know where it's been and how to get back to that place, or an animal that might say, oh, there was a source of food someplace, how do I get to it? Or there was a danger, how do I get to it? Or there was a mate, how do I get to them? There was a big evolutionary advantage to that. So early on, there was a pressure to start understanding your environment, like where am I and where have I been? And what happened in those different places? So we still have this neural mechanism in our brains. It's in the mammals. It's in the hippocampus and entorhinal cortex. These are older parts of the brain, and these are very well studied. We build a map of our environment. So these neurons in these parts of the brain know where I am in this room and where the door was and things like that.
So a lot of other mammals have this.
All mammals have this, right? Okay. And almost any animal that knows where it is and get around must have some mapping system, must have some way of saying, I've learned a map of my environment. I have hummingbirds in my backyard, and they go to the same places all the time. They must know where they are. They just know where they are when they're not just randomly flying around. They know particular flowers they come back to. So we all have this. And it turns out it's very tricky to get neurons to do this, to build a map of an environment. It's just, and so we now know there's these famous studies that's still very active about place cells and grid cells and these other types of cells in the older parts of the brain and how they build these maps of the world. And it's really clever. It's obviously been under a lot of evolutionary pressure over a long period of time to get good at this. So animals know where they are. What we think has happened, and there's a lot of evidence to suggest this, is that mechanism we learned to map like a space was repackaged. The same type of neurons was repackaged into a more compact form, and that became the cortical column. And it was in some sense genericized, if that's a word. It was turned into a very specific thing about learning maps of environments to learning maps of anything, learning a model of anything, not just your space, but coffee cups and so on. And it got sort of repackaged into a more compact version, a more universal version, and then replicated. So the reason we're so flexible is we have a very generic version of this mapping algorithm, and we have 150,000 copies of it.
Sounds a lot like the progress of deep learning.
How so?
So take neural networks that seem to work well for a specific task, compress them, and multiply it by a lot, and then you just stack them on top of it. It's like the story of Transformers in
but it's interesting. Deep learning networks, you're replicating an element, but you still need the entire network to do anything.
Right.
Here, what's going on is each individual element is a complete learning system. This is why I can take a human brain, cut it in half, and it still works. It's pretty amazing.
It's fundamentally distributed.
It's fundamentally distributed, complete modeling systems. So, but that's our story we like to tell. I would guess it's likely largely right, but there's a lot of evidence supporting that story, this evolutionary story. The thing which brought me to this idea is that the human brain got big very quickly. So that led to the proposal a long time ago that, well, there's this common element, just instead of creating new things, it just replicated something. We also are extremely flexible. We can learn things that we had no history about, right? And so that tells us that the learning algorithm is very generic. It's very kind of universal because it doesn't assume any prior knowledge about what it's learning. And so you combine those things together and you say, okay, well, how did that come about? Where did that universal algorithm come from? It had to come from something that wasn't universal. It came from something that was more specific. And so anyway, this led to our hypothesis that you would find grid cells and place cell equivalents in the neocortex. And when we first published our first papers on this theory, we didn't know of evidence for that. It turns out there was some, but we didn't know about it. And since then, so then we became aware of the evidence for grid cells in parts of the neocortex. And then now there's been new evidence coming out. There's some interesting papers that came out just January of this year. So one of our predictions was if this evolutionary hypothesis is correct, we would see grid cell place cell equivalents, cells that work like them through every column in the neocortex. And that's starting to be seen.
What does it mean that, why is it important that they're present?
Because it tells us, well, we're asking about the evolutionary origin of intelligence, right? Yeah. So our theory is that these columns in the cortex are working on the same principles. They're modeling systems. And it's hard to imagine how neurons do this. And so we said, hey, it's really hard to imagine how neurons could learn these models of things. We can talk about the details of that if you want. But but there's this other part of the brain we know that learns models of environments. So could that mechanism that learns a model of this room be used to learn a model of the water bottle? Is it the same mechanism? So we said it's much more likely the brain's using the same mechanism, in which case it would have these equivalent cell types. So it's basically the whole theory is built on the idea that these columns have reference frames and they're learning these models, and these grid cells create these reference frames. So it's basically the major, in some sense, the major predictive part of this theory is that we will find these equivalent mechanisms in each column in the neocortex, which tells us that's what they're doing. They're learning these sensory motor models of the world. We're pretty confident that would happen, but now we're seeing the evidence for it.
So the evolutionary process, nature does a lot of copy and paste and see what happens.
Yeah. There's no direction to it, but it just found out like, hey, if I took these elements and made more of them, what happens? And let's hook them up to the eyes and let's hook them up to the ears. And
that seems to work pretty well, like for us. Again, just to take a quick step back to our conversation of collective intelligence, do you sometimes see that as just another copy and paste aspect? Is copying and pasting these brains in humans and making a lot of them and then creating social structures that then almost operate as a single brain?
I wouldn't have said it, but you said it and it sounded pretty good.
So to you, the brain is is its own thing.
Yeah, our goal is to understand how the neocortex works. We can argue how essential that is to understanding the human brain, because it's not the entire human brain. You can argue how essential that is to understanding human intelligence. You can argue how essential it is to sort of communal intelligence. Our goal was to understand the neocortex.
Yeah. So what is the neocortex and where does it fit in the various aspects of what the brain does? Like, how important is it to you? Well,
obviously, again, I mentioned again in the beginning, it's about 70 to 75% of the volume of a human brain. So it dominates our brain in terms of size, not in terms of number of neurons, but in terms of size.
Size isn't everything, Jeff.
I know, but it's nothing. It's not that. We know that all high-level vision, hearing, and touch happens in the neocortex. We know that all language occurs and is understood in the neocortex, whether that's spoken language, written language, sign language, whether language of mathematics, language of physics, music, math. We know that all high-level planning and thinking occurs in the neocortex. If I were to say, what part of your brain designed a computer and understands programming and creates music, it's all the neocortex. So then that's just an undeniable fact. But then there's other parts of our brain are important too, right? Our emotional states, our body regulating our body. So the way I like to look at it is, can you understand the neocortex without the rest of the brain? And some people say you can't, and I think absolutely you can. It's not that they're not interacting, but you can understand it. Can you understand the neocortex without understanding the emotions of fear? Yes, you can. You can understand how this system works. It's just a modeling system. Mm-hmm. I make the analogy in the book that it's like a map of the world. And how that map is used depends on who's using it. Mm-hmm. So how our map of our world in our neocortex, how we manifest as a human depends on the rest of our brain. What are our motivations? What are my desires? Am I a nice guy or not a nice guy? Am I a cheater or am I, or not a cheater? Mm-hmm. How important different things are in my life. But the neocortex can be understood on its own. And I say that as a neuroscientist, I know there's all these interactions, and I want to say I don't know them and we don't think about them. But from a layperson's point of view, you can say it's a modeling system. I don't generally think too much about the communal aspect of intelligence, which you've brought up a number of times already. So that's not really been my concern.
I just wonder if there's a continuum.